Just a bit of a, one of those sections that sometimes are a little bit of an issue. But as I said, what we're going to try and do, just make a brief introduction, and then thereafter, obviously try and tackle as many questions as we possibly can together, right? Please, I say this again, you're allowed to stop me at any time should there be any question. Okay, we're clear with that, right?
Yes.
All right, awesome stuff. Right, now let's go right into it. Right, I'm going to share my screen in just a few. Right, so what I want to do quickly is maybe you just go through, the 9 theorems that are found in grade 11. And then quickly what I'm going to do thereafter is just make sure that we do as many applications as possible, of these theorems. Okay. Right. Please just note them down. You don't have to write everything. By the way, these sessions are recorded. And if you want to access the recording, just let us know. What I'll do is that I'll load them up on YouTube as private links, and then you can have access to those private links. Okay. You don't have direct access to it. I'm sure you guys are already aware that I've got a YouTube channel, so you can just go on to the channel, but we will give you links to these sessions because obviously they are private. Okay, right, now let's go right into it. So Euclidean geometry, let's start with the first theorem. So when we talk about theorem 1, okay, theorem 1 simply states, now we're going to talk about circle geometry, of course. The others I'm just going to make an assumption for now, but of course we'll build this up as we go along, right? So in this case, theorem 1 simply state, if we've got a line that is drawn from the center, okay, and in this case what it does is that it bisects a chord, right? Now this is called a chord. So a line that is drawn from the circumference to the other side of the circumference is called a chord, right? In this case, what it does, once you draw a chord, it divides the circle into what we call a segment. So this part is called a segment, okay? Now, if you've got a smaller segment like this one, we call it a minor segment, right? And of course, what this means is that we also have what we call a major segment. Okay, so right, so we've got a major segment on the other side, right? So in this case, please just remember, theorem 1 says if we've got a line, okay, that is drawn from the center of a circle, right? Yeah, I just erased that mistakenly, right? If I've got a line that is drawn from the center and it bisects a chord, in this case, we know that it means that that line is perpendicular. Okay, right. Notice we say, well, if we call this line AB, and it means that at C, if I tell you that AC is equals to CB, then what it means is that if I've got a line that is drawn from center, it means that that line would be perpendicular to that chord. Now, there's a converse of theorem 1, okay? And the converse of it is as follows, right? If I still have a line segment, okay, or in this case, if I've got a line that is drawn from the center, note how I'm stating it, right? If I've got a line that is drawn from the center, and in this case, it is perpendicular to a chord, therefore, it bisects the chord. Notice the difference between how I stated the theorems, right? I said this one, if I've got a line from center on the first one, line from the center, that bisects, meaning that cuts a chord into two, right? So if I tell you that AC is equal to CB, that is a given, right? So now you can conclude, if it's a line that's drawn from the center, you can conclude that, well, it means that let's call this O. So it means that OC is therefore perpendicular to AB. In this case, the converse of the theorem, if I've got, there's my AB again, there's my OC again, now I am telling you that if I've got a line, okay, if I tell you that OC is perpendicular to AB, right, therefore you can conclude that AC is equal to CB. All right, please note. So that is our theorem 1. Theorem number 2 is as follows. Right, we're going to apply these in just a few. Né? So theorem number 2 is as follows. It simply says, well, once I draw an angle that is subtended by an arc. Now, I'm not going to make these difficult. Né? That's not the point. So if I've got an angle that is subtended by a chord, in this case, then the angle at the center, now notice this, the angle at the center of the circle will be equal to the angle at the, twice the angle at the circumference. Now, if I call this angle X, let's call this A, B, C, okay? And let's call this O. So it means if the other angle touches at the circumference of the circle, then it means that angle AOB is equal to 2 times the angle ACB. I hope that is, so we say angle at center is equal to twice angle at circumference. Now, please, I want you to note, please be warned. Sometimes they might give you this theorem and, or rather they might give you in a structure, they might give you something, let's say, that looks like this. Please note, you cannot apply this theorem there. Why? Because this angle here is not touching the circumference of the circle. All right. So we can only apply this theorem to if the angle is touching the circumference of the circle. Okay. Right. So we say angle at center is equals to twice angle at circumference. Now let's talk about theorem 3 quickly. So theorem 3, okay, again, we've got a circle. Now we say in this case, if the angle is subtended, so meaning there's our angle there, okay? So we say if the angle is subtended by a diameter, now let's call this ABC. So if AB is a diameter, so in this case, we know that if the angle C is subtended by a diameter, it will actually be equal to 90 degrees, right? So we say when we state this theorem, we usually say this is angle at semicircle, right? So this is angle at semicircle, right? So we know that angle at semicircle would be equal to 90. Now, if you want to notice, in this case, this is the same application as the previous theorem. Now, if you note, a straight line is always 180 degrees. This is our angle at center, right? Now, notice this, the angle at circumference would therefore be 90 degrees. And notice, we said angle at center is twice the angle at the circumference. 90 times 2 would give us 180. So we say that this is right. So in this case, sorry about that. So we say that in this particular case, then angle at center is equal to twice angle at circumference. But the correct way of stating this, we say this is angle at semicircle. Right. Let's go on to theorem 4, and we're going to be moving quite swiftly because I want us to cover as much ground, doing past questions, okay, applications rather applying the theorems so that I show you some nifty ways of going through that. Right, now theorem number 4. Please let me know if I'm going too fast. Okay, right, now in this case, what we said is, well, what we are saying rather, is that if we've got angles that are subtended by the same arc, okay, right, notice in this case, let's say we've got arc, or rather a chord, right? Now remember, an arc in this case is this part of the circle. We call this an arc, all right? And remember, that's a line segment. So please don't be thrown off by these terms. Né? So what we are simply saying is that they are subtended by the same arc in this case. So it means that angles that are subtended by the same arc are equal. Okay, all right. Or you can simply just say angle at same segment. Okay, they're on the same line segment. So in this case, it means that those two angles are equal. Okay, right. So just another way of stating the same thing. This would be another way of proving that it's a line is a cyclic quad, or rather, we've got a cyclic quad. But we'll talk about that once we get there. But another way of applying the same theorem is if we simply say, well, if we've got equal chords in this case, right? If our chords are equal, so let's say we've got two chords there, and I say, well, this chord here is equal to that chord. I'm telling you that, right? Now, once we draw an angle that would touch the circumference, all right, like that. So in this case, if I've got equal chords, then what it stems to say is that the angles that are subtended by equal chords are also equal. So in this case, it means that this angle here would be equal to that angle there. But what we simply say is that they're subtended by equal chords. Are we okay?
Yes.
All right, beautiful stuff. Let's go to theorem 4. Right, I want us to be done. Theorem 5 rather. Theorem 5. Now from theorem 5, I want you to note now we are entering, just the theorems that literally, or in fact, from theorem 4, I should say, we are dealing with cyclic quads. Okay. Now, theorem 5 simply says that if we've got a cyclic quad, now note cyclic quad, it means that it's a four-sided figure wherein all the vertices, meaning all the sides or the angles, right, of that, the four corners rather, touch the circle. So it's not a cyclic quad if one of the corners does not touch the circumference. Okay, so this wouldn't be a cyclic quad. Why? Because this corner here does not touch the circumference. Okay, so in this case, what you simply are going to say is that let's say we've got cyclic quad A, B, C, D, right? Now, what we say is that the opposite angles of a cyclic quad are supplementary, right? So what does that mean? It means that angle B plus angle D would be equal to 180 degrees. Okay, but what is that? We say these are opposite angles of a cyclic quad. Okay, right. So opposite angles of a cyclic quad. So this angle here plus that angle there equal to 180, but what it also means is that angle A plus angle D would be equal to 180 for the same reason as well. Okay, now theorem 6. So we're looking at theorem 6. Right, so when you look at theorem 6, what we simply say is that once we've got angles that are, or we say the exterior angle of a cyclic quad, okay, is equal to the opposite interior angle. Now, sorry about that. I think I may have to just get water. Right, so we've got A, B, C, and D. Let's call that E. So let's call this D1 and D2. Right, now D2 in this case would be equal to angle A, sorry, because if you think about it, in this case, we say that this is the exterior angle of a cyclic quad. But think about it. If you had this angle becoming x, what would be this angle? It would be 180 minus x, and that would be because of sum of angles on a straight line, isn't it? Right? But also, what this means is that now, because this one is 180 minus x, this angle D1 plus that angle A would be equal to 180. So it makes this one to be equal to x as well. Okay, so that's another way of us stating that. So we say this is the exterior angle of a cyclic quad. Okay, a cyclic quad. All right, so we know that they are equal. Now let's go to theorem 7, and all of these now include radii, no, actually tangents. Theorem 7. Now, theorem 7 simply says if we've got a circle, right? And in this case, we've got a tangent. Now, what is a tangent? It's a line that touches the circle once, right? So there's our tangent there. But if we were to draw a line from the center that meets with the tangent in this case, so it means that where they meet with the tangent at the point of tangency, they would be perpendicular. All right. So they say the tangent of a circle, rather, is perpendicular to the radius at the point of tangency. That's very important. Only at the point of tangency. So meaning that at no other point except where the tangent meets the circle. So we call this the 10 radius theorem. So you can just write it like this, the 10 radius theorem, right? And of course, if we find that we've got a line, the converse of it is that if we've got a line that is drawn that is perpendicular to the radius through a point, okay, so it means that line would be a tangent. So in this case, if we've got a line, a radius, right, and we draw it and we find that it's perpendicular, it means at the circumference, so it means that that line that passes there would be a tangent. Okay, right, now theorem 8, as I did say, I'm trying to rush as quickly as possible so that we go to the application. Now theorem 8, again, this involves tangents. Okay, what this simply says to us is that if we've got two tangents, okay, I'm trying to get them to meet, and they meet at a point outside the circle, right? So once those two tangents meet at a point outside the circle, we say, well, in this case, it means that the length of those tangents from the point of intersection, right? So if I say this is A, B, and C, then it means line AB would therefore be equals to line BC. Okay, and in this case, we say, well, we know that they are meeting at a common point, which is C, which is outside the circle. So it means that those tangents must be equal. Now, the last one, which is theorem 9, and we are going into application, right? Theorem 9 simply states, in this case, we call this the 10 chord theorem, right? The 10 chord theorem. So if we've got a tangent, and we've got a chord. In this case, we know that the tangent, all right, maybe let me just write this down first. Now, please, I want you to note, ladies and gents, this is quite a popular theorem. Ne? So if I've got, let's say this is A1, 2, and 3, and let's call this B and C, right? So what this means is that angle A1, notice, so this is our tangent, this is our chord, this is the angle opposite that chord. Okay, so in this case, it would mean that A1 is equal to angle C, and we call this the 10 chord theorem. But what it also means is that if I look at A3, right, here's our tangent, there is our chord, there is the angle opposite that chord, and in this case, if this is going to be A3, A3 would therefore be equal to B, and all we simply state there is this is the 10 chord theorem. Okay, we know once we've said that, then it means that those angles are equal. All right, if you want to state it in full, it says the angle between the tangent to a circle and a chord drawn to the, from the point of tangency is equal to the angle opposite the circle segment. So in this case, the angle opposite, right? So there's a segment, the angle opposite that segment. Okay, right. Now, ladies, let's go into the application of this. Now, is there anything that you'd like to ask regarding the theorems? All right, shall I assume that we are all good? All right. All right, beautiful stuff. Let's take the first question. And I've sourced this from a past exam question paper that a grade 11 past exam question paper, right? Now, sometimes we find applications where they give us the angle, but sometimes they don't, right? But in this case, if they do, obviously what we do when it comes to circle geometry, please always try and work within the diagram as much as possible. Now, ladies, I want to state this categorically, right? How do you get good at Euclidean geometry? Well, you can only be good when you obviously apply it as much as you possibly can, right? There is absolutely no way that you can be good at it by just watching me do the questions, okay? At a point, I will send these questions over to the group. Please just make sure that you can do these questions on your own, okay? Right, now, now they say in the figure O, O is the center of the circle, right? Now, immediately when they say that, what should I do, right? I know in this case, what does it mean for me? What it simply means is that this side here is equal to that side there. Why? Because they are radii, isn't it? It means OD is equal to OC, it's equal to OB, it's equal to OA. So already that is important information for me, and I'm going to use that as much as possible. Okay, right. Now they told me that O is the center, A, B, C, D, and E lie on the circle such that chord AB and chord DC are equal. They've indicated that to us, right? Now, ladies, I want you to note, I have got equal chords. What does that say to me? If I were to call this angle X, right? So if I call this angle X, what does this mean? It means this angle would also be X. Why? Because I've got angles that are subtended by equal chords. Do you remember that equal chords thing? Right? So I've got angles that are subtended by equal chords. So it means that those two angles would actually be equal. All right. Now, Let's also note there, they said an AEB is equal to 39. All right, now, the first thing that they ask us, they say determine the size of O1. Okay, right, please work with me. How can I get the size of O1? Okay, anyone who wants to take a bite at it? Okay, all right. Let's. Yes. Is there someone?
Okay.
Okay, Bonolo. Yes.
So I think O1 will be 78 degrees.
Okay, why?
Um, the angle at the center is
Ah,
twice.
beautiful, beautiful. So we are now applying that angle at center theorem, Mangetina. So we know in this case, it means that the angle at the center, remember they are subtended by this arc AB, ne? So we're saying angle at center is equal to 2 times the angle at circumference. So you're saying to us, Bonolo, O1 would be equal to 2 times angle angle E, right? Or rather angle EAB or AEB rather. And you said the reason angle at center equal to 2 times angle at circumference, ne? At circle. All right. So that would mean this angle here would be 2 times 39. And you said that's 78 degrees. Correct. And therefore, now we know, ne? So we know O2 is equal to O1. But why is that? So this is 78 degrees. But why is that? Why is O1 78 degrees? Because we said they are angles that are subtended by equal chords, right? Angles that are subtended by equal chords. All right.
And can we also use vertically opposite angles as a reason?
No, you can't. Now, that's a very important question, Bunolone. That's a very important question. Remember, if you look at line DB, right? Do you see it's actually it's not a line? Do you see that that's not a straight line? Remember, vertically opposite angles can only be used if I know that these are straight lines. So let's say I've got AB and I've got CD, right? So in this case, what this means is that we've got these angles as vertically opposite. Now, why you couldn't use vertically opposite there is that if you look at from D to B, that's not a straight line. It kind of bends a little bit there. Do you see? Nalo?
Yes, I see.
Okay. Yeah. So in that case, we couldn't use vertically opposite. So the only way, and that's why it's very important to remember these theorems, ne? The equals chords theorem, in this case, if they are subtended by equal chords, then it means that those angles are also equal as well, right? So it means that O2 would therefore be equal to O1. Why? Because they are subtended by equal chords. All right. So as a result, it means that O1 would actually be equal to 78 degrees as well. Okay. Right. So they said determine the size of O2. Well, we've already done that. We found both O1 and O2. Now, if I were to ask, ladies, maybe let's ask Ashley. Ashley, if I wanted to find the size of angle C, what would be the size of angle C? And why? I'm not putting you on the spot, ne? Okay. Bushle?
Sir,
Yes. Is that Ashley or Rubus?
it's
Oh, that's
Ashley.
Ashley. Yes. Yes. What would be the size of angle C? Or how would we determine the size of angle C?
Okay, wait, let me first calculate this. So I'm not sure.
Okay. Now, can I ask what type of triangle is OCD? Do you see that's an isosceles triangle? Because we've got OC equal to OD. Why? Because they are radii, right? Radii. So we've got OC equal to OD. Why? Because they are radii. So in this case, what this means is that, therefore, triangle OCD is an isosceles triangle, right? Is isosceles. Okay. Now, I want you to note, once we've got an isosceles triangle, we already know that this angle here is 78. Now, it means the base angles, so therefore, it means that angle D must be equal to angle C, right? And why? These are base angles of an isosceles triangle, of an isosceles triangle, right? Right. So angle D is equal to angle C. So in this case, this would be, if you wanted to call this, let's call it, angle Y, right? So it means in triangle OCD, right, you would have angle O2 plus C plus D being equal to 180 degrees, right? But what is O2? O2, remember, we know is 78. C and D are equal because they are both Y. So this would be 2Y. This is equal to 180, right? So it means that 2Y would be 180 minus 78. I think that would give us 102 degrees. And so in this case, if I wanted to find Y, you'd say, well, divide that by 2. And in this case, that would give us 51 degrees. Does that make sense, Ashley?
Yes, sir.
All right. So that's why I said, when it comes to Euclidean geometry, and the fact that I went through the 9 theorems in grade 11 does not discard the work that you have already done in grade 10. Okay. Your isosceles triangles, your, all the types of your equilateral triangle. You must know that all the sides are equal, but it means all the angles are equal and therefore equal to 60. Okay, angles on a straight line, that's also important. Exterior angles of a triangle. All right, awesome stuff. Now, let's move on to the next question. Are there any questions?
Yes, sir.
Yes, go ahead.
For the angle O2 plus C, what would be the reason
plus C plus D equals 180.
Oh, sorry, I didn't state the reason there. It's sum of angles on a triangle. So we always say, oh goodness, my pen is misbehaving. Right, so we always say these are angles on a triangle. You don't need to write a lot of things. We know sum of angles on a triangle are equal to 180. So I took this angle here, plus that angle, and all of them are equal to 180. Okay. Happy days, ne? All right, you good, Ashley? All right. Bushle,
Yes, sir.
are you good?
Yes, sir.
All right, awesome stuff. Okay, let's go on to the next question. I wanted us to take another question. Now, they say in the diagram, O is the center of the circle. Okay, and they say that chord AC is perpendicular to radius OD. Okay, at B. And they say that OB, sorry, is 2x and AC is 8x. Now they say to you, show that the length of BD is 2x multiplied by that whole thing. Now, how do we think we are going to do that? Maybe let's ask you, Bushe, what can we deduce from this? Let's start working from the drawing itself. Okay, right. Don't try to answer the question just yet. Let's just work with what we know. What can we deduce from this diagram? And please don't be afraid. Okay, Bushe, do you agree with me? We can use theorem 1, or rather the converse of theorem 1. They already told us that that is a center, right? Okay.
Yes.
Yeah, this thing is really giving me an issue. Maybe let me just get it off. Right. They already told me that O is a center, right? So now if it's a center, and look at that, it makes a 90 degree there. What did you say about theorem 1? We said a line that is drawn from the center that is perpendicular to a chord, what does it do? It bisects the chord, right? So it therefore tells me that it means AB is already equal to ABC. Does that make sense?
Yes.
Right. So now, also, do you agree with me that OA, right, I'm trying to write this down. So OA would be equal to OC. Do you agree?
Yes.
Okay, what would be the reason for that? Oh, by the way, equal to OD as well. Do you agree with me, Uti? All of those are radii. It means obviously the radius of a circle, all the radii of the circle are equal, right? Does that make sense?
Yes.
Okay, beautiful stuff. Now let's fill in what we know. They told us that OB is 2x. So they told us that this guy here is 2x. And they told us that AC is 8x. So what it does is that because AC is 2x, what it does is that it makes this guy here to be half of that, because we said they are bisected at B. So it means that's 4x and 4x. Do you guys agree with me?
Yes.
All right. And now remember, what are we looking for? We are looking for BD. All right. Now, okay, so how are we going to go about that? All right. Would it be possible for me to find a length OC? Is it possible?
Yes.
What can I use? Pythagoras, isn't it? Right?
Yes.
Because I know the length of this guy is 2x, right? I know the length of that guy is 4x. But remember, before I do that, I need to state all of that. And that's the thing about Euclidean geometry. For every single step that I take, I need to always give a reason, right? Now, let's start here. We said, look, because we've got a line that is drawn from the center, it means that AB is equal to BC, right? And why did we say that? In this case, we know that OB is perpendicular to AC, right? AC, which was given, right? Or in fact, I should have started with that. OB is perpendicular to AC, which is given. Therefore, state this. So therefore, it means that AB is equal to BC. Okay, right. In this case, a chord, line from center that is perpendicular to a chord, in this case, bisects the chord. Okay. Are we all together?
Yes.
Now OB is 2x, and that was given. Yes.
OB is perpendicular to AC. Is that my reason?
OB perpendicular to AC. No. So I said we can actually write this down first, right? So let me remove this and say, let's write that down first. That in this case, OB is perpendicular to AC. And what is the reason? It's that it is given, right? Now, therefore, if it's perpendicular, it means that AB would be equal to BC. Now, remember, that's the converse of theorem 1, okay? Right? And the converse of theorem 1, remember, AB is equals to BC. In this case, we simply say that it's the line that is drawn from the center, okay? Line from center, center that is perpendicular to the chord. Are you with me now? So you don't need to write the entire theorem. Just say line from center that bisects a chord. We know, that is perpendicular to a chord. If it's perpendicular, it means that it bisects. Are you with me, Ash?
Yes, sir.
Right. So now I'm going to work, it doesn't matter which of the two triangles, né? Okay, I'm looking for a little bit of color, right? So I'm going to work within this triangle and say, look, I'm looking for the line OC. Do you agree with me that OC squared would therefore be equal to OB squared plus BC squared, right? But I already know OB is 2x 2x squared. BC is 4x squared. Oh, by the way, we didn't state why that line is no, actually we don't need to, because we've already stated that they are equal, and therefore it means that they will bisect that line. Okay, so BC is equal to 4x. Ladies, are you still following?
Yes.
Okay, so this will give me 4x squared plus 16x squared. So in this case, this will be 20x squared. So this is what? This is OC squared, right? Now, in this case, please note that OC, this line here, is actually equal to OD, right? So OC is equal to OD. But why is that again? Radii. Okay? Because it's from the center to the circumference, it means it's a radius, right? Okay. Was there a question? Yes.
Yes. For Pythagoras, why did we end at 20x squared?
Okay, you can actually just try to simplify it there. We can say, well, OC would therefore be equal to, let's try and simplify it. 20 would be 4 times 5, right? You always use 4 times 5x squared. So if I take the square root of that, in this case, square root of 4 is 2. So this would be, OC would be actually 2 square root of 5x. Does that make sense? Ashley?
Yes, sir.
Okay, right. So all I simply did, I wrote that 20 as 4 times 5. And the reason I wrote it like that is so that, you always try to break it down into prime factors. So that's 4 times 5, so that I'll have 2 square root of 5. Né? Okay, even if you were to put it in your calculator, I'm sure you were going to get exactly that. Square root of 20. Okay, if I write it in, there, 2 root 5. Can you see it? All right. So in this case, you've got 2 root 5 of x. Now, remember, what are we looking for? We are looking for BD. Ah, man. We're looking for this side BD. But remember that OD is a radius. That's what we said, right? It's a radius. And we already know what the length of the radius is. It's 2 root 5. So it means that OD is actually composed of what? It's composed of OB. So to get that whole length there, it's OB plus BD. Does that make sense? This plus that gives us the whole of that. So OD is equal to OB plus BD. Are you all together with me, ladies?
Yes, sir.
All right. Now, in this case, we already know the length of OD. We know this is going to be 2 root 5 of x. We already know the length of OB is 2x. That's 2x. And we wanted the length of BD. Okay? So let's take the difference in that case. So BD would be equal to 2 root 5 of x minus 2x. Okay? Now you can see we can take the common factor on both sides, which is 2x, right? So if I take out 2x as a common factor, what am I left with here? I'm left with root of 5 minus, in this case, 2x multiplied by what will give us 2x? minus 1. And so there we've proven it there. All right. Does it make sense, ladies?
Yes, sir.
All right. Okay, I want us to move on to the next one. As I said, ladies, I want it to be, if there's anything that I want out of these sessions, is that we should try by all means to, cover as much ground when it comes to Euclidean geometry. I want you to apply it as much as possible so that, you are able to, to deal with questions in that regard. Okay, right. I think we've covered. Okay, we'll come to that in just a bit. I think that would be the last one. All right. Now, let's take this one here. Okay. Right. Now they say in the diagram S, right? I'm trying to show you how we're always going to be applying these theorems, right? In the diagram S is the center. So again, they're telling us that's the center. Okay. Of PQRT. Now again, they're telling you that PT is a diameter, okay? And of course, they're giving you something there. RST is x minus 8. And they're also giving you, PQR, which is 2x minus 40. Right. Please help us out. How can we get the value of x here? Right, I'm just going to give you just a few minutes to think about it, and then I want us to just look at the solution together.
Sir,
Yebo.
what is the first question we're starting with?
What's the first question that I did what?
Oh no, it's fine.
Okay. So the
so-
question is just determine the value of x.
So we can work with exterior angles of a cyclic quad.
Correct. But you have to know that you are dealing with a cyclic quad. Remember the warnings that I gave you, né? It has to touch all four vertices. All four vertices have to touch the circumference of the circle. All right. Bonolo?
Yes.
Have you made means?
So ngicabanga ukuthi P will be half of S.
Okay. Now, please remember, Bonolo, né? Remember that theorem will only be applicable. Please remember, if they are subtended by the same arc? You see, are they between the same arc?
No.
No. Okay, so we can't apply angle at center is equal to twice angle at circumference here, right? And to answer Ashley's question, Ashley, oh, this screen is a little harsh on my eyes. Okay, Ashley,
Yes, sir.
we also couldn't apply the exterior angle of a cyclic quad. Why? Because
It doesn't touch all four sides.
correct. It's not a cyclic quad if one of the vertices does not touch the circumference. Unless if the examiner had told you specifically that PQRS is a cyclic quad. Are you with me now? So we're going to have to be a little bit creative on this one. And how are we going to be creative? I'm going to make a construction line. Okay? Right? And I'm going to say, well, let's draw line RT. And look at that. What happens when I draw line RT? Sorry about that. Right. What happens when I draw line RT? What makes PTRQ? What is PQRT?
A cyclic quad.
Correct. So now I've got a cyclic quad. Can you see that? So sometimes you might find that if you're not able to apply your theorems, so you might need to be a little bit creative and just make a construction line. Okay? So now, by the way, now that I've got a cyclic quad, what can I now say?
So,
Yes.
wait. I would say no. Okay, I would have said that 2x minus 40 is equal to S1.
Where is S1?
The one inside, not x minus 8. The other one on the other side.
Oh, okay. So you call this S1? Okay, yes.
So I would have said 2x minus 40 plus S1 is equal to 180 opposite angles of a cyclic quad.
Say that again.
2x minus 40 plus S1 is equal to 180 opposite angles of a cyclic quad.
I see. But remember that PQRS is not a cyclic quad. Please keep that in mind, né? Okay. Now let's try and go through it together, né? Now, please remember, try and exploit as much as possible. So if I told you that this is a radius, what does that mean? What does that mean? Which sides are equal? Do you agree with me that ST is equal to SR? Do you agree?
Yes, sir.
All right. Why?
Because of equal radii.
Radii, right? And do you also agree that it's equal to P? Even if you're not going to use it, just note all your lines that are equal. Okay. So in this case, it means that ST is equal to SR, which is equal to SP, right? And what do you notice there? It means that all of those are actually radii, they are equal. Okay, right. So we've drawn line RT such that we know now that PQRT is a cyclic quad. We don't need to prove that because it touches all the is a cyclic quad, right? We don't need to prove it because all the four sides actually touch the circumference. Okay, now what we noticed there was that, but we also know that now look at angle Q and angle T. What do you notice about those? They are opposite angles of a cyclic quad, isn't it? Do you agree with me?
Yes, sir.
So I can say angle Q plus angle T, that's equal to 180, right? And what's the reason? These are opposite angles of a cyclic quad. Okay, so these are opposite angles of a cyclic quad. Are you with me now? So in this case, we can find angle T. So what is angle T? T would be equal to 180 minus, notice, what is angle Q? That's 2x minus 40. So let's try and find an expression for that. So that means that would be 180 minus a minus 40, or let's say minus 2x plus 40. In this case, it means angle T would be 180 plus 40. So that would be 220 minus 2x. Do you all agree with me?
Yes, sir.
Okay, so we've got angle T, right? Now, if we know what angle T is, now look at this. What kind of triangle is triangle RST? What type of triangle is triangle RST?
An isosceles triangle.
Correct. So in triangle RST, we know that RS rather is equal to ST, right? That's radii. Okay, so therefore it means that angle R must therefore be equal to angle T. And why is that? These are base angles of an isosceles triangle. Okay, these are base angles of an isosceles triangle. Does that make sense, ladies?
Yes, sir.
Okay. Right, so now we are working within this triangle RST. So we know, we found this guy to be 220 minus 2x. We found this guy to be 220 minus 2x. And we know this one is x minus 8. So we can take the sum of angles on a triangle, isn't it? All right, so I can just simply say, well, it means that we are still working within triangle RST. So in triangle RST, we are going to have angle R plus angle S plus angle T equal to 180. And you can say these are angles on a triangle. Okay, sum of angles on a triangle. So now we've got angle R, which is 220 minus 2x. Okay, angle S which is x minus 8, but angle T is the same value, which is 220 minus 2x, and this is equal to 180. Are we all good, ladies?
Yes, sir.
All right, now, obviously, let's try and find that. So this is going to be 440, okay, minus 8. So that's going to be 432. Okay, I'm working with these. 440 minus 8. That's going to be 432. And I've got minus 2x, which is minus 4x, plus x, that's going to be minus 3x, is equal to 180. So take this to the other side. I've got minus 3x is equal to 180 minus 432. Okay, I'm a bit lazy now. So it's 180 minus 432, and that's minus 252, right? So minus 3x is equal to negative 252. And so what is our value for x? Divide both sides by negative 3. And so it means that x would be 252 divided by 3, and that gives us 84 degrees. Okay. Ladies, please tell me that made sense. All right. So just going back to what we did. Remember, you cannot conclude. So my point was, Ashley, we cannot conclude that something is a cyclic quad, or rather a quadrilateral is a cyclic quad, if, first of all, if we are not told, and secondly, if the 4 vertices are not do not touch the circumference. Okay. And my second point was, sometimes if we find ourselves in a predicament where we cannot apply any of the theorems, right? There is a need, there might be a need for us to make a construction line that would help us to solve the question. Okay. Are we happy, ladies?
Yes, sir.
All right. Beautiful stuff. Okay, just the last one, and I think we're going to call it a day for today. Okay. I wanted you to just take a look at this one. I want you to work within the diagram as much as possible. Just answer the first question, all right? So the first question just has to do with the size of angle Q1. Okay, try and work as much as possible within the diagram. See which angles are equal, all right?
Sir,
Yebo.
what did you say? What should we determine?
So the size of the first question I think was on the size of Q1. The size of Q1. Did you find it?
No, not yet.
Okay. All right. I'd like for us to continue. Okay, let's just try and work through the diagram together, right? So, Bonolo? Okay,
Yes.
okay. Let's try and work through it. Okay, maybe, or let's try Ubuhle. I think it's been a while since we didn't hear her voice. Buhle?
Yes, sir.
Yes, what were your discoveries?
Sir, I'm not sure, but I said that S1 is just a second. I said S1 is equal to Q because of exterior angles of a cyclic quad.
Okay, I love it. I love it. I love it. Okay, so you actually realized, okay, I'm gonna just use a different color here. You realized that you've got a cyclic quad here. This guy here would be this guy here is a cyclic quad, right? Okay, so now that being a cyclic quad meant that 48 degrees would be the exterior angle of a cyclic quad. Very well done, Bushe. So that would be the exterior angle of a cyclic quad. So that would mean it's equal to the opposite interior angle. So it means those two angles there are 48 degrees, right? Okay, very well done. Okay, what else?
Sir, are you able to say that Q1 is equal to 24?
Yes, because you were given that Q1 is equal to Q2, right? So in this case, if both of them are equal to 48, then it would obviously mean that each one of them would therefore be equal to 24 degrees. Very well done again. Okay, what else? I want us to work within the diagram as much as possible, just identifying angles that are equal or angles that have a particular significance and so on and so forth. Right? Any other thing?
Sir,
Yes. And by the way, any one of us can contribute. Né?
yes, sir. If Q1 is equal to 24, then R is also equal to 24.
Ah, okay. And why is that?
Angles in same segment.
Correct. So that would be equal to 24, right? What else? Don't forget that O is the center, right?
Angle P is equal to 90 degrees.
I
Reason,
love it. I love it. So angle P is 90, but why?
angles in a semicircle.
Correct. Correct. So that's 90 degrees. But what else?
Angle N is also 90 degrees.
Angle N is also 90 degrees. Correct.
Yeah.
Reason?
Angles in a semicircle.
Correct. Okay. I said we are working within the diagram as much as we possibly can. So I'm going to leave the, giving the reason, obviously answering the question to you, but I just wanted us to work within the diagram as much as we possibly can. Right. Any other angles that we would know of? The size of angles that we would know of. Please, as I said, you must never forget you've got radii, right? Always try to exploit the fact that you've got an isosceles triangle, right? So what would be the size of angle, let's call it P1?
So wouldn't it be 24?
Yes, but why is that, Ashley?
Alternate angles.
Oh, yes, I think you can also use alternating angles, right? Alternate angles in this case, because you've got parallel lines, these would be alternating angles. But remember also, because they are base angles of an isosceles triangle. So if you look at triangle OPQ, right, that's an isosceles triangle because you've got those two equal sides. So it means that this would also be 24 degrees. You are quite correct, Ashley. Which other angle? Would you agree with me that S3 would also be equal? Say that again.
Wouldn't S3 also be equal to 24?
Correct. Why?
Basis of an isosceles triangle.
Correct. So you are now working with triangle ORS, right? Okay. But you could have also used alternate angles. In this case, it means that that Q1 would also be equal to S3, right? Okay. Now, do you agree with me that we would also be able to determine, if we call it P2, just for argument's sake, this P2 guy would be able to find out what the magnitude of P2 is, because then it means P1 plus P2 gives us 90. If we know this guy is 24, we just have this one as 90 minus 24, right? So I think that would be 66 degrees, this guy over here. Okay, 90 minus 24. And then, yeah, you can work with as much as you possibly can. What would be this angle over here? Let me not write it in the same color. What would be the magnitude of this angle over here, right? It would be 180 minus 24 minus 24. So it would be 180 minus 48. And in this case, that would be 132, I think. Okay. Yeah, so you can play around with this as much as you possibly can. Now let's look at the questions quickly. They say determine the size of Q1. All right. Q1, we found out it's 24. But obviously, I mean, you'd need to work through that. We started from the 48-degree angle, and we said, well, look, exterior angle of a cyclic quad, Q1 and Q2 gave us 48 as well. And in this case, you've got the 2, half of that is 24, because Q1 was equal to Q2. So we got Q1 to be 24 degrees. And then they said the size of R, we already found that. We said it's also 24. You used, I think it was it Ubonolo or Ubuhle, where you said angle at same segment. Okay. Now, we would be able to find angle M1. Let's see, how would we find that angle M1? So we would know, right, corresponding angles, right? Corresponding angles, please don't forget. So if that guy is 48 there, right, they are parallel lines. So it means that this guy would also be 48 because they are corresponding angles. Okay. Right. And then they say prove that ST is a tangent to the circle. Okay. Passing through M, N, and S. Okay. So in this case, we know that we would have, where is that? ST is a tangent. Okay, so where is ST? ST, sorry, there it is there. Is a tangent passing through M and S. Where is M? Okay, so it means we can actually use the 10-chord theorem there, right? Because remember, by virtue of this being equal to that, we can use 10-chord theorem and say it means therefore they are also equal. Okay. Right. Ladies, was that helpful?
Yes, sir.
All right. Beautiful stuff. Okay. I'm looking forward to us meeting again tomorrow. And please remember that the recordings of this will be made available in case you guys go through load shedding. I've got backup on my side, so I'll always make it a point that the recordings are available. Thank you so much, and I'll see you guys tomorrow. Okay.
Bye.
All right. Sure.